Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Interview questions in chemical engineering. Heat transfer part 2. I would appreciate if you subscribe to the channel, which is striving hard to deliver valuable knowledge content for your career progress. So subscribe now before you forget. For every question, you are given 20 seconds to think about your answer. Then the answer will appear. Check your answer is correct. Wherever required, detailed explanation is given. Knowledge of heat transfer is essential in any chemical industry, particularly so in refineries and petrochemical plants. In the last video in this heat transfer series, we discussed 5 questions with answers. So we will start with question number 6. Question number 6. What are the types of condensation? Which type is normally experienced in the industries? Which condensation will have higher heat transfer coefficient? Explain why. Your time starts now. Your time is up. The answer. Condensation occurs by two different mechanisms, namely dropways condensation and film condensation. The nature of the condensation depends upon whether the condensate or the liquid formed from the condensation process wets or does not wet the solid surface of heat transfer. If the liquid or the condensate wets the surface and flows on the surface as film, it is termed film condensation. When the condensate formed from the vapors does not wet the solid surface and accumulates as droplets, it is called dropwise condensation. This figure illustrates the two types of condensation processes. The figure A describes the film condensation process, where the vapor on coming into contact with the colder heat transfer surface condenses. The condensate formed wets the surface, and a film is formed by the condensing vapor as shown. In the figure B, the vapor comes into contact with the colder surface and condensation starts. In this process, the condensate does not wet the surface, and hence droplets are formed as shown. Dropwise condensation needs a polished or clean surface. This requirement is difficult to meet in industrial applications where the heat transfer surface is rarely clean, except during the startup period due to fouling or accumulation of dirt on the surface. Hence, the nature of condensation is normally film condensation. In the film condensation process, the continuous liquid film formed on the surface provides stronger resistance to heat transfer. The thickness of the film formed depends on many parameters, including orientation of the surface, viscosity, or rate of condensation, etc. The rate of heat transfer is reduced because of this thermal resistance. For this reason, the heat transfer coefficient is 4 to 8 times higher for dropwise condensation as compared to film condensation. Question number 7. How does a thermosyphon reboiler work? Your time start now. Your time is up. The answer. The flow through the thermosyphon reboiler takes place due to the density difference between the density of the liquid in the feed inlet pipe to the reboiler from the bottom of the distillation column and the two-phase vapor liquid mixture in the reboiler return line to the column. This figure illustrates a vertical thermosyphon reboiler. Within the reboiler, the liquid and vapor are in intimate contact with each other. So the vapor and liquid returning to the column are in equilibrium. However, inside the column, the liquid is mixed with the liquid coming from the bottom tray, which will have higher concentration of more volatile components than the returned liquid. Thus, the liquid that forms the bottom product has more volatile components than the liquid that is in equilibrium with the returned vapor from the reboiler. Note that in the figure shown, there are two compartments at the bottom of the column separated by a baffle, vertical baffle. The one compartment on the right side serves as the reboiler liquid compartment. The other compartment on the left side serves as a bottom product draw compartment. In a vertical thermosyphon reboiler, the boiling occurs inside the tubes. The steam enters the shell side at the top and the condensate is removed through a nozzle at the bottom of the shell. The differential pressure or the head required for liquid circulation through the reboiler is obtained from the expression delta P, the driving force, equal to 1 by 10,000 into H1 rho 1 minus H2 rho 2 minus H3 rho 3. This expression is derived with reference to the figure 1 shown before. Where delta P is a differential pressure expressed in kg per centimeter squared. H1, H2 and H3 are the head in meters as shown in the figure 1. Rho 1, rho 2 and rho 3 are the densities in kg per meter cube of reboiler, inlet liquid, outlet two-phase mixer, inside reboiler two-phase mixer respectively. As a conservative estimate, the density of the liquid vapor mixer inside the reboiler rho 3 is taken as an average of rho 1 and rho 2, that is rho 1 plus rho 2 by 2. Note that the elevation of the reboiler inlet nozzle from the column bottom, that is H1, is a critical parameter to be determined at the time of design. The frictional losses in the system include friction losses in the piping from the column bottom to the reboiler inlet nozzle, delta P1, friction losses across the reboiler, delta P2, friction losses in the vapor piping connecting the reboiler and column nozzle, delta P3. The total friction losses in the reboiler circuit thus is equal to delta P equals delta P1 plus delta P2 plus delta P3. The thermosyphon circulation is maintained if the driving force delta P is greater than the total friction losses in the circuit delta P. Since the driving force for circulation through the reboiler arises from the density difference, the magnitude of force is not very large enough to overcome any additional resistances over and above what is considered in the design as explained above. In practice, frictional resistances develop during operation due to fouling on the tube side. The fouling deposits adds to the system frictional resistance and reduce the circulation rate. Hence, for such fouling services, thermosyphon reboilers are not suitable. Another situation where the thermosyphon reboiler application is not recommended is for viscous fluids. For a given vertical reboiler circuit, the frictional resistance of high viscous liquid is higher compared to the low viscous fluids. This increases the head required for natural circulation, which creates practical engineering issues, hence not recommended for viscous liquid. Question number 8. In a thermosyphon reboiler shown in the sketch below, if you are asked to increase the vaporization rate, what action you will take and what are the limitations? Your time starts now. Your time is up. The answer. Since the system layout, that is the column, reboiler and the connected piping is fixed, the driving liquid height is fixed. The pipe diameters are also fixed. Thus the system resistances cannot be decreased. Hence the only way to increase the evaporation rate is to increase the temperature difference. Since the column pressure is fixed, the boiling temperature of the liquid cannot be changed. It will remain at 55 degrees centigrade. The only variable that can be manipulated in this case is the hot water temperature. Increase of hot water temperature will increase the heat transfer rate. Hence, the vaporization and circulation can be increased. However, pressure drop increases with increasing vaporization rate. That will decrease circulation rate. At some point, say beyond 80 to 85 degrees centigrade, the increase in driving force is compensated by increasing pressure drop across the reboiler and the connector piping loop. Beyond this, pressure drop becomes dominant. There is a risk of system instability. The system limitation has been reached. Question number 9. What is fired heater? What is the principal modes of heat transfer in a fired heater? Your time starts now. Your time is up. The answer. A fired heater is a direct fired heat exchanger that uses the heat of combustion to rise the temperature of a feed flowing through coils of tubes aligned throughout the heater. It is a chemical reactor in which fuel and air undergo exothermic reaction to produce the required heat. It is a special variant of a shell and tube heat exchanger consisting of a furnace and a row of tubes installed inside the furnace through which the process fluid flows. The principal modes of heat transfer in a fired heater is by radiation and convection. The large share of heat transfer is by radiation. Question number 10. What do you understand by fouling in heat exchangers and its impact on heat transfer process? How it is taken into account in the heat exchanger design? Your time starts now. Your time is up. The answer. Fouling is mainly defined as the formation of deposits on heat transfer surfaces due to sedimentation, crystallization, biological growth, chemical reactions, corrosion products, freezing, or their combination. Fouling will result in decreased thermal performance because of additional resistances to heat flow. As fouling formation occurs, the heat transfer capacity of the exchanger decreases. This figure illustrates the temperature profile in a countercurrent heat exchanger. As the heat transfer surface in a heat exchanger is fouled, due to the additional resistance to heat flow, the heat transfer coefficient decreases. Hence, the available area of the given heat duty is not sufficient. As a consequence, the hot stream outlet temperature increases and the cold stream outlet temperature decreases. This will indeed affect the production process. The fouling of a heat exchanger can be monitored via the overall fouling resistance RF. RF is defined as the difference between dirt and clean overall heat transfer resistances. RF is written as RF equal to 1 by UD minus 1 by UC, where UD and UC are dirt and clean overall heat transfer coefficient. Technically speaking, inclusion of fouling factor RF will result in lower overall heat transfer coefficient, hence a larger heat transfer area, which can be inferred from the expression below. The heat transfer area is expressed as the heat transfer rate Q divided by the dirt overall heat transfer coefficient times LMTD. Due to the fouling resistance, U has become lower. Accordingly, as per the expression, A will be larger. Thus, fouling factor is expressed as a design margin M as an additional percentage of heat transfer area. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.